All right, your final test is called the root test. Now, what the root test is helpful with is if you have powers of n, but it's not a geometric one. Obviously, if you saw something like this, you would know it would be a geometric test because n is the power. But what happens if there's more going on with the power of n? Well, that's where our root test here says that if we take the nth root of our series, which is the same as the 1 over n power, and take the limit as n approaches infinity here, it's the same rules as our ratio test. If the limit is smaller than 1, it will converge. If the limit is greater than 1, it diverges, and if it equals 1, it's inconclusive. So let's finish our lesson with these next 3 problems. We know that there's no necessarily one right test for everything, so we could have done our ratio test for this, but the fact that both numerator and denominator have a power with n in it means we can do the root test. What that looks like is we're going to take the limit as n approaches infinity, and we are going to nth root our series. And what the nth root does, think about this as like powers and roots undo each other. So this nth root cancels out the n powers. So this is actually equal to 2 squared, which is 4 over n. And now when we plug in our infinity, we get 0. Our rule said that if this is less than 1, it converges. So this looked like a tricky series at first, but once we do the nth root and then we apply our limit as n approaches infinity, it's the same rules as what we just did. And technically it's the absolute value of our answer, but because we just got 0, it's 0. Okay, let's see this with the next one. Again, this looks like a really tricky thing. There's a lot going on. It's not just geometric because it's not a constant in the parentheses. What we can do is we can do the nth root, let's do the limit as n approaches infinity. And it's the nth root of our series. So that 4n minus 3n cubed over 5n cubed plus 1 all to the power of n. And I love this one because this nth root cancels out the power of n, leaving us with the limit as n approaches infinity of what was left under the root and power. And we can see that our highest term, the power of 3, means we can take the coefficients here. And so it will be a negative 3 over 5. And again, that's where the absolute value comes in. The fact that our coefficients are less than 1 makes this converge. Okay, our final problem to solve may not look like a root test. It was really easy with the other ones to identify it as a root test because they both had a power of n, or the numerator and denominator had the power of n. And this one, only the numerator has the power of n. But we can still apply it. Let's see what happens. When we do the limit as n approaches infinity, we'll do the nth root of our given problem. What this does, this cancels out the numerator's n, but remember, the root n is the same as something to the 1 over n power. So even though this n root didn't cancel anything in the denominator, what we actually have here is n to the 4 over n power. And why might we do that? Well, there is a rule that says when we plug in infinity, this will now be negative 2 over infinity to the, we have an n there, 4 divided by infinity is 0. And anything to the 0 power is 1. So this is negative 2 over 1. And remember, we need the absolute value. And so what we actually get here is 2. I'm going to go ahead and erase this part here. And if the limit is greater than 1, we diverge. So it didn't look like a root test, but you can make it into a root test and then just apply it with infinity. Okay, there we have it, our last test. I know there are some problems I didn't go through in this video, but these are ones I would have skipped in class anyways, so this is what you need for topic 22. If you have questions, feel free to message me or find me at school on sometime at school on Friday. Okay, have a great rest of your day.